Okay, here's another example of using binary variables in modeling in a linear program. And so this one, we're blending oils at a kind of food production, blending the raw oils. We've got 5 different types of oil. 2 are vegetable-based oils, three are non-vegetable-based oils. Go ahead and read through the scenario here. Okay. Pause the video. Think about how many of these constraints you can come up with on your own, and then we'll kind of come back together and try it. Okay. So give it your best try first, and then unpause and continue. So here's how I went ahead and solved it. First, for kind of notational purposes, or just to kind of make things easier, I'm going to have kind of an I index. Give your index a different name. And I'm just going to number these oils 1, 2, 3, 4, and 5. Saves me writing out veg 1, veg 2, oil 1, oil 2, and oil 3. Okay. I can kind of put those same numbers down here as well. Looking at the parameters of the problem, these are the prices. And so I'll call those sort of price of I. And then down here, the oil has a hardness rating. I'm not an expert on oils, but we'll call those hardness of I. Okay, and so those are sort of the 2 vectors of parameters that I have in play here in this problem. Similar to the last problem, we're going to want to introduce paired variables. One to say how much of each oil to use, and another one to record whether or not we use that oil or not. Okay. In this case, we don't have setup costs, but we still want to have those paired variables because some of our constraints will work much better with a binary yes, no, did we use that oil, as opposed to the how much of that oil did we use. Okay, so let's go ahead and define our decision variables. And we'll have, I'll kind of follow the kind of, I don't know if it's a widely used one, but at least for me, I like to name my continuous variables X and my binary variables Y. Just kind of helps me keep them sorted. So XI is we're using large units here, tons of oil of type I equals 1 to 5. Okay, where 1 to 5 kind of moves through veg 1, veg 2, oil 2, and oil 3. And then yi is going to be the corresponding binary variable that equals 1 if xi is positive and 0 if xi equals 0. Okay, so this is the corresponding binary variable for that continuous variable. Okay. So those are the decision variables. Let's go ahead and talk about the objective. So when we sell it, it sells for $180 per ton, regardless of what we mix into it. Okay, so the revenue side is going to be kind of fixed. The price side, we've got different price per oils, and we noticed that all these cost less than $180 per ton, and so we're definitely going to have a decent profit margin no matter which oils we're using, but we of course want to maximize that profit. Okay. So let's go ahead and take that into account. Our objective is that we want to maximize profit, and that profit is equal to, well, let's think of for each ton of oil that we sell, we get the profit, which is, or the revenue, which is 180, minus the price of that oil that went into it. And that's going to be multiplied by X of I. Okay, and so if we use a ton of the first oil, then when we sell it, we're going to get 180 dollars per ton that's in this XI variable, minus the price that we paid per ton on that oil. Okay, and then we're going to sum this up over each of the 5 oils. Okay, and so yeah, this here is essentially the net profit per pound of oil used for each of the oils, where it's 180 is the revenue minus the price that we paid for it. Okay, that's the objective. Now let's move on to the constraints. This one has a few more constraints than the last one, so I'll go ahead and move on to a new sheet of paper because we've got quite a few constraints going on. The first constraints we'll deal with are the sort of what I'd call the conditional constraints that tie the X and corresponding Y variables together. So here, let me write. So here's our constraints. First one, we'll do our conditional constraints that essentially define our Y variables. And that is that xi should be less than or equal to, I'm going to leave a little blank here, yi. Okay, and now we want to think of, okay, what's the most that we can do? Okay, and actually, we're also going to kind of let this, yeah, so what's the max of each oil that we could produce? Well, that kind of comes in, if we're reading the paragraph, the total amount of vegetable oils that we can produce is 210, and the total amount of non-vegetable oils all combined is 260. And so kind of taking the larger of those two, we know that any individual oil we won't create more than 260 tons of any individual oil. And so we can use that in here as our big M. So this is sort of the big M in that constraint. Okay. We know that any individual oil, we're not going to make more than 260. And some of the oils, we couldn't even make more than 210. For simplicity, you could just kind of choose the larger of the two and use it for all of them. And so we can do that for I equals 1 to 5. Okay. There's another constraint that sort of gives us a lower bound. And if we're reading this, we got these bullet points at the bottom here. And this second bullet point says that if an oil is used, at least 30 tons of that oil must be used. So they don't want us kind of just dripping in a little bit of oil of one type in there. If we're going to use it, we got to use a significant amount of it. And so we need to use at least 30 tons. That's actually going to look a lot like this. So we'll call that minimum oil used. And that's minimum if we use it, right? We can still have them be 0. And so we want to kind of write this constraint in such a way that we still allow both yi and xi to be 0. But if they're non-zero, particularly if yi is equal to 1, then xi has to be bigger than 30. And the way we can write that is that xi has to be bigger than 30, but only if yi is equal to 1. Yi is equal to 0, we're essentially going to turn off this constraint. So this is maybe very similar into our tips and tricks of how to turn off a constraint when we have to only kind of satisfy some, but not all. And so actually we're going to turn it off by multiplying it by yi. Okay, so if yi is 0, that will actually force xi to be 0 up here. And then this constraint will then say 0 is greater than or equal to 0 and will be feasible. Okay. If yi is 1, then this constraint means that xi has to be greater than or equal to 30, which kind of enforces that minimum if we're using the oil. And so that's going to be 4i equals 1 to 5. Okay, so we'll get 5 copies of that one. We have some limits on refinement. That's what I was mentioning a little bit earlier, in that we can only refine 210 tons of vegetable oil and no more than 260 tons of non-vegetable oil. And so this is going to be 2 constraints, one for vegetable oil and one for non-vegetable oil. And so for vegetable oil, we've got our 2 vegetable oils are X1 and X2. And the total amount of vegetable oil has to be less than or equal to 210. And then for non-vegetable oils, that's the other 3 plus X4 plus X5, and that has to be less than 260. Okay, that's a plus there. So the sum of the non-vegetable oils has to be less than 260. The sum of the vegetable oils has to be less than 210. Okay, and just one of each of those. No sort of indexing involved in that constraint. Next constraint, now we're getting down into sort of the bullet points at the bottom. These are maybe the kind of tricky ones in this problem. We already took care of the second one of the bullet points there. Now let's maybe go ahead and take care of this first one, which is the food may never be made up of more than 3 oils. Okay, and so our yi records whether or not we use that oil, and we only want to allow essentially 3 or fewer of the yi's to be 1. If there's a 4th yi that's 1, that's not allowed. Okay, and so I may write this down as at most 3 oils. And we'll write that as the sum over the yi's has to be less than or equal to 3. Okay, so there's 5 y variables. At most 3 of them can be 1. It's possible to make it solely out of a single oil if we wanted to. Not going to end up being optimal to make it out of a single oil, but potentially it might make sense to make it out of 2 oils. We'll see. So, so that's at most 3 oils. Now let's maybe check out off this one, which says that if either veg 1 or veg 2 are used, then oil 2 must be used. Okay, this is what we call a contingent constraint. Anytime you see an if then, probably thinking about a contingent constraint. And so y1 and y2 are what control this. And if either of them are used, then oil 2 must be used. So I'll kind of copy that down. If veg 1 or veg 2 then oil 2 must be used. Okay. There's maybe a couple different ways you could encode this. I just did it as two separate constraints. Veg 1 is y1 and oil 2 is y4. And if I just do oil, y1 is contingent, or yeah, y1 forces y4. is essentially the way I think through this, in that if y1 equals 1, then y4 must also be 1 and oil 2 must be used. Similarly with y2, we'll also force y4 to be 1. Okay, so these are kind of both y1 or y2 pushes up y4 is sort of the way of kind of pushing up is turning on maybe, and pushing down is turning off. You'd also think of that y4, if it's 0, turns off both y1 and y2, which sort of almost guarantees that we're going to use oil 2 in this, because otherwise we'd be eliminating all of our vegetable oils from the mixture. And being that we get sort of profit per ton of oil used, and if we kind of completely eliminate vegetable oils, we're probably not going to make our most profit from this product. Okay. So the last constraint is probably the trickiest, which is having to do with blending. Okay. For blending, as it's sort of, we're going to have to take into account this hardness. And we want the overall hardness to be between 3.5 and 6.2. And it says, assume that hardness blends linearly. And what we mean by that is not that, is essentially that you can take the overall hardness is going to be the sum of each of the hardness times the proportion of that oil. Okay, and so maybe I'll write out what it means for it to blend linearly. It essentially means that overall hardness equals each of the individual hardness, so hardness of I, times proportion of oil I. Okay, and then we'd sum over each of the I's. Okay, let's maybe think about what this proportion of oil I is. That's going to be XI. That's going to be the amount of oil I used divided by essentially the total amount of oil used. And sort of the total amount of oil used is going to be, well, here, I'll maybe write it out. X1 plus X2 plus dot, 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 plus X5. Okay, and so this is that. Okay, so that's the overall hardness by combining the individual hardness and our variables here. Okay, and we want that overall hardness to be between, well, really this is two constraints. So we want the overall hardness to be greater than or equal to 3.5, and also we want that overall hardness to be less than or equal to, what is it, 6.2. Okay, so we get two constraints. Sometimes you'll sort of see mathematicians sort of write upper and lower bounds on both sides of that overall hardness. Just remember that when you actually program it into the computer, you can't have those compound inequalities. You need to sort of separate that out into separate inequalities. Okay, if we were trying to take this and just plug it in here, or really this whole formula, and plug it in here, you'd notice that we'd have division of variables by variables. And that wouldn't work actually very, very well at all. And so the trick is we actually multiply through by the denominator here. Okay. And when we multiply through by the denominator, it essentially cancels it on the left side with the overall hardness. And the left side becomes the sum over I of hardness I times the top of the fraction was just xi. And that has to be greater than or equal to 3.5 times this denominator that now we've multiplied over. I'll kind of note that that denominator is just the sum of the xi's. And so maybe I'll put parentheses around it and sum over I x I. Okay. Similar sort of thing's going to happen with the other one. We'll notice that we sort of have all the decision variables on both sides of this equation. OMPR is perfectly fine with that. I will maybe kind of point out a neat little trick, especially going to be important if you sort of have to write out the constraint matrix, which assumes that you get all your variables to one side, is we can kind of rearrange this and bring these over this side by subtracting them over. And then kind of combine the sums because they're actually adding over the same thing, and just sort of figure out that the coefficient of each xi is going to be the hardness minus the lower bound target for that hardness. And so this then becomes the sum over I hardness of I minus that lower bound of 3.5. And then that's being multiplied by xi. And that has to be greater than or equal to 0. Okay. Similar thing's going to happen for the upper bound. So maybe I'll bring that over here. I'm going to write it in this format because I think it looks nice and compact, though OMPR would perfectly accept it if you wrote out something that looks like this, where you swap this to be a less than or equal to and change this to be a 6.2. And so that'd be sum over I. This time I'll do upper bound minus hardness. And so 6.2 minus hardness of I times xi, and that's going to be greater than or equal to 0. So if you did it in the same order of hardness minus 6.2, then it'd be less than or equal to 0, and the sign and the direction would be flipped. But because we do upper bound minus the hardness, that's going to be greater than or equal to 0. Okay. One thing to note is that some of these individual oils are actually outside the lower bound and upper bound. And so actually some of these terms in here are actually going to give you negative values. Negative values in this one if the hardness is smaller than the lower bound, and negative values in here if the hardness is higher than the upper bound. Okay. And so we're going to get both of these constraints for each I1 to 5. Okay, and so that's all the constraints for this problem. We've got sort of our conditional constraints that set up the kind of relationship between the x and the corresponding y variables, minimum oil used, limits on the amount we can refine, at most 3 oils being used, the condition, the kind of contingent decision on if either veg 1 or veg 2 are used, then oil 2 must also be used. I'll maybe make one comment here. You could combine these into a single constraint if you wanted to, by saying essentially the OR of veg 1 and veg 2 in this case would be y1 plus y2. Times a half. Okay, if you go back to the bag of tricks, that's actually half of what you need for the OR, but because we're just using it in a less than, we only need the push up side of the OR, and that's got to be less than or equal to y4. Let me just kind of look at this and verify. Yeah, so if y4 equals 0, then the sum of these two positive things has to be less than or equal to 0, so they both must be 0. On the other hand, if either of these is 1, then you're going to get 1/2 on the left side, and if it's bigger than a half, it has to be 1. So, yeah. I guess you could combine both of these into this and that'd be equivalent. Or maybe it's easier to think about this, and so maybe do this. So shouldn't make too much of a difference for this size of problem. If you're dealing with thousands of constraints and efficiency is important, then yes, kind of think about these quick savings, but otherwise maybe choose the more readable and understandable choice of constraints instead of the maybe more compact version. And then we've got our blending constraint, which are sort of, this is all explanation up here. These are the two constraints we end up with for each I 1 to 5. Okay, let's go ahead and implement this in R. Okay, here's the R code. I've gone ahead and created some vectors for the price and the hardness. I've also sort of coded up the hardness upper bounds and lower bounds in here. I like doing this anytime there's parameters of the problem, though you'll notice I sort of left some numbers still in the problem there. Probably could have put the revenue and the upper bounds and lower bounds up here as well. But I like doing that because then I can just change the numbers at the top, rerun all the code, and it should still run. So I've got my X and my Y variables, 5 copies of each of them. I've got my objective where I'll take 180 minus the price, and that's the net profit per ton of oil used. Here are my kind of conditional constraints for my binary variable. Here's the minimum oil if used. Here's the limit on vegetable oil refined. Here's the limit on non-vegetable oil refined. Here are the sort of if veg 1, then oil 2, and if veg 2, then oil 2. So I kind of coded them up as separate constraints in the actual code. This is the no more than 3 oils used, being the sum of the yi's is less than or equal to 3. And then lastly, these are our blending constraints. The lower bound and the upper bound on hardness are coded up there. So let's go ahead and run this code chunk and see what the output gives us. And so we maximize profit with $34,000 worth of profit. We end up making 180 or blending 180 tons of the first vegetable oil and 30 tons of the second vegetable oil with 260 tons of the fourth vegetable oil, which is then oil 2. Okay. Notice that since we did use the vegetable oils, X4 was forced to be positive, or actually Y4 was forced to be 1, which then forced X4 to be at least 30, but it ended up going up to its maximum, and we ended up not making any of X3 or X5. Okay, interesting that we made both the 2 vegetable oils. I think that actually had to do with the blending constraint, because if you look at the hardness of the oils, the first veg oil is very hard and is over that sort of upper bound of hardness. And veg 2 is right at the boundary of that upper bound for hardness, and oil 2 is at the lower end, but not the lowest. And so by mixing in some veg 2, it sort of is able to stay within the bounds of that upper bound of hardness constraint. Also note that oil 2 is very cheap, and so it makes sense that we use a lot of oil 2 in the product. And I guess veg 2 provides more profit per ton. So interesting that we use so many tons of veg 1. Okay, yeah. That's maybe the reason why we build optimization problems to optimize this, is because it's maybe not always obvious just by looking at it where you should be blending your oils or which oils you should be blending. So that's it for this video. See you in the next one.